Well, so far, you guys, we've kind of dealt with some simple um, series, and that have special characteristics in order for convergence test to be applied. Um, but any slight deviations can make the test non-applicable up to this point. So, for example, if you look at these 1, 2, and 3, this first one, this is geometric, so we can use the geometric series test. This one looks like it's pretty similar, but it's not, so I can't use the geometric series test for that. Right? The second one, I could do a p-series with it. This one looks pretty similar, but I can't use p-series test on that, and so on. Right? This one could be easily integrated. That one cannot, and so on. So we're going to be given 2 additional tests today. These are for positive term series. So we'll have the direct comparison test and the limit comparison test. And this will expand what we can test for convergence and divergence, because we can take a messier series and compare it to something similar or simpler. Okay, so we'll start with the direct comparison test first. If you want to read through the proof, you're welcome to. I'm not going to go through that, but what this direct comparison test will do for us is with our given with the given a sub n as our given series, and if the number one there, if the bn, which is larger, converges, and maybe you want to write this, if the larger series converges, okay, bn is, the terms are all larger than an, then the smaller series must also converge. Okay, so that's the number one. The second one there, let me do it in a different color, black. This is saying, well, if the smaller series diverges, remember an is smaller than bn, if the smaller series diverges, then the larger one must diverge. Okay, let's do an example so we can kind of see this. Determine the convergence or divergence of 1 over 2 plus 3 to the n. Well, this series resembles the more simple 1 over 3 to the n, which is a geometric series, right? This is a geometric series. You could write that as 1/3 to the n. That's the same thing, right? So it's 1/3 to the 1, 1/3 plus 1/3 to the square plus 1/3 to the third, and so on. So our common ratio is a third, and since the common, by the geometric series test, since that's less than 1, by geometric series test, converges. All right, we know this 1 over 3 to the n converges by the geometric series test. So a term by term comparison yields, we have a to the n, which is 1 over 3 to the n plus 2. This will always be less than, all of its terms will be less than 1 over 3 to the n, which is my b to the n, for all n greater than or equal to 1. right? For example, with 1/3 to the n, you'd have 1/3, you'd have 1/9, 1/27, and so on. Whereas you'd have 1/3 plus 2, 1/3 squared plus 2, and so on. Can you see how these ones are all less than the ones above it, right? 1/11 is less than 1/9, and so on, right? So term-by-term comparison shows us that a sub n is less than b sub n. Well, since the larger series converges, then we know the smaller series, the original series, must also converge, right? And so we can conclude, since larger series converges by the geometric series test, then smaller series must converge. And let's just therefore by the direct comparison test, this series converges. That smaller series converges. Let's take a look at this next one here. We're also going to use a direct comparison to something a little simpler. Notice this resembles something that we could use the P series with. So this resembles, let's just do 1/√n, right? Which, by the P series test, you get 1/n to the 1/2, right? So 1/n to the P. Our P is 1/2, so that is less than or equal to 1, greater than 0, diverges. So it diverges by P series. Now the problem is, we have a to the n, which is 1/2 plus root n. It's less than 1/√n. But Bn is larger, right? Bn is larger. And again, we want, it's larger and diverges. So this does not meet the requirements of the test. Remember, we want it to be smaller and diverging. If it's smaller and diverging, then the larger one diverges, right? But this is larger and diverges. So it does not meet the requirements. Oops. Of the test. Well, let's still go with this being diverging. Still expecting the series to diverge. Let's compare it to the harmonic series, 1/n, which diverges by the P series. You get P is 1 here. So it also diverges. So note, you would have, if you were writing this out, you'd have 1/1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and so on, right? Now our original a sub n, if I was writing that out, I'd have 1/2 plus root n, so 1/3, And I'd have 1 over 2 plus the square root of 2. And then I'd have 1 over 2 plus square root of 3. Oops, that's a really bad 3. 1 over 2 plus the square root of 4. And so on. And if I was, that's 0.3 repeated. That's 1 over 2 plus root 2. I'd punch that in. Over here, I'd punch this one in. 0.268. That's 0.25. 0.236, and so on. So you notice that until it hits n being 4, after greater than or equal to 4, the harmonic series is smaller, but not until that fourth term, fifth term, right? On the fourth term, they're the same. After 4, no problem. So let's write this. So we have this harmonic series which diverges. We have a smaller one being less than 4 and greater than 4. Therefore, since we know 1 over n diverges, that's the smaller one. The smaller one's diverging. So it's kind of like, well, we can ignore it because we know this is going to infinity. Ignore the initial terms. After that, since the smaller one's diverging, the larger one must diverge because all terms after 4 are smaller. So. All right, we're going to compare this series to 1 over n cubed, which by the p-series test, p equals 3, so p is bigger than 1, it converges. And so a term-by-term comparison will yield, we'll have, this will always be less than 1 over n cubed for all n that are natural numbers. In other words, for all n greater than or equal to 1. Therefore, since the larger one converges, we know the smaller one must also converge. And so therefore, by the direct comparison test, the series converges as well. Let's start out with a little analysis of this one here. We know, we know cosine bounces back and forth between -1 and 1, right? The values of cosine. And so if we add 1 to that to get the cosine of n plus 1, our numerator, if I add 1, then we'd have 0 less than or equal to cosine of n plus 1 less than or equal to 2, right? So we have our cosine n plus 1. Well, let's divide all this by n squared. And so we have 0 less than or equal to cosine n plus 1 all over n squared less than or equal to 2 over n squared. And so then the discussion is, should we let Bn be the one on the left or the right? Of course, zero's on the left, so it's really not much help, right? But we want to think about convergence or divergence. So we're going to let that B of n. So we will use B of n to be that 2 over n squared. Since we know by the P series, 2 over n squared, let me write it this way, well, that's 2 times 1 over n squared is the same thing. So 2 times 1 over n squared. So we know by P series, P equal n to the 2. P is the 2, so we got P being greater than 1. It converges by our P series. And so the larger one converges. We know the smaller one must also converge, right? The original given one. So a term by term comparison will give us this. We know that's less than or equal to 2 over n squared, so B of n. Therefore, since the larger one converges, the smaller one must also converge. Here we've got natural log of n over n plus 1. Actually, that's supposed to be from 2 to infinity on this. And I want to note for a minute the graphs. Let's think about the natural log of x for a second. Here's our natural log of x. I'm also going to graph y equals 1. I'm also going to graph y equals just the line y equals x. So here's y equals 1. Here's the natural log of x. It goes through 1, 0. There's our natural log of x. And finally, here's y equaling x. And this is the point right here. This is the point e comma 1 right there. So natural log of e to the 1 is just 1, right? And notice here, why I graph this is for values that are greater than or equal to 3. Actually, write this down. Notice for n greater than or equal to 3, the natural log of n, see how it's in between the 1 and the y equals x right there? For n being greater than or equal to 3. So if I divide that, remember we have the series is ln of n all over n plus 1. So if I go over n plus 1, everything, of course this is greater than 0. These are positive terms. Remember, these tests are for positive terms. So, that's where we're at. Now we have an ability to compare these, right? And so what we're going to do now is if we let, so then it's like, do we roll with the left or the right? Well, let me roll with the left for a minute. A little simpler there. If we let Bn be the 1 over n plus 1 for a minute, then we can use, let's use the integral test from last time. All the terms f is positive, continuous, and decreasing. And so 2 to infinity of 1 over x plus 1 dx, which should be the same as the limit b goes to infinity from 2 to b. And I'm going to go ahead and let u be x plus 1. So this is 1 over u. So I'll have the limit as b goes to infinity. The integral of 1 over u is the natural log of u from 2 to b. So we've got the limit b goes to infinity, the natural log of b plus 1 minus the natural log of 2 plus 1. Well, this is going to go to infinity. So this thing ends up diverging. So, and let's write that. So by the integral test, it diverges. Well, that was our smaller. It was smaller than the ln of n over n plus 1, right? So if the smaller one diverges, the larger one's got to diverge. Therefore, ln of n over n plus 1 from 2 to infinity also diverges by direct comparison test. So second comparison test referred to as a limit comparison. So, sometimes you got a series that looks like maybe a p-series or geometric, but we can't establish a term-by-term comparison for that last test, that direct comparison. So that's where this comes into play. It'll take a very messy algebraic series with like a p-series or geometric series, and it's a nice comparison. It's a second comparison test. And so what you do is you take the original an and you divide it by bn. And then if it gives you a value that's positive, then if the one you compared it with converges, then the original converges. If the one you compared it with diverges, then the original diverges, and so on. If it equals 0, then the one you compared it with converges, then you can conclude the original converges. And if it shoots to infinity, then they both diverge if the one you compared it with diverges. Okay, so let's run that. So let's do it. Let's do it for just a general harmonic. I know a and b are usually values here, but we can so by comparison with b of n, where our b of n is just 1 over n. So we're comparing it with this series, okay, which is a harmonic series, and by the p series test, 1 over n to the p, so p is 1, where p equals 1, so p is less than or equal to 1, greater than 0, it diverges. So that's what we're going to use b of n with. And so now we can using the limit comparison test. So what we'll do is we'll run the limit as n goes to infinity of the original over the one we're comparing it with. So we got 1 over an plus b over, we're comparing it to 1 over n. And so we'll multiply by the reciprocal. So 1 over an plus b times n over 1. So we got n over an plus b. Notice we have infinity over infinity. So let's do this algebraically though. We'll divide everybody by n. So 1 over a plus b over n. Remember, a and b are just values, right? They're positive values, real numbers. So as I run this to infinity, this will go to 0. So I'm just left with 1 over a. Again, remember a is positive. Well, by this limit comparison test, can you see how we got 1 over A, which is positive, and we knew the one we compared it with diverged, so the original must diverge as well. This is positive. So therefore, by limit comparison test, since we had the one we compared it with diverges, I'll write it out, and equals some value which was greater than 0, then the general harmonic original also diverges. Okay. A little commentary here. So it's really nice when you're comparing a messy algebraic series with a P series, right? So here's our given series. You compare it to like a 1 over n squared. You run that, the original over that, limit as n goes to infinity. You're going to see they both converge. And that's because this one converges, right? And so that's kind of the approach that you have. There's a couple others as well. And so the trick is, when choosing a series for comparison, disregard all but the highest powers of n in both the numerator and denominator is kind of what you're thinking about there. Okay. So let's look at this one. So disregarding all but the highest powers of n in the numerator and denominator, we can compare with, so square root of n over n squared, okay, which is 1 over n to the 3 halves. If I clean that up, which by the p-series test, p is 3 halves, so that means our p, whenever our p is bigger than 1, it converges by the p-series. 1 over n to the p, right? Converges by the p-series. So now we can applying the limit comparison test yields the limit as n goes to infinity, a to the n over b to the n. So get the limit of our original over the one we're comparing it to, which is 1 over n to the 3 halves. And so I'll have a square root of n over n squared plus 1 times n to the 3 halves over 1. So I got n to the 3 halves times n to the 1, n to the 4 halves, which is n squared. So I got n squared over n squared plus 1. And by that's infinity over infinity, so I'm going to use L'Hopital's rule. So limit n goes to infinity. So I'll have 2n over 2n plus 0. Again, infinity over infinity, so I'm going to use L'Hopital's again. Derivative of the top is 2, derivative of the bottom is 2. So it looks like I get 1. What do I care about? Well, it's when I run it, I do get something positive, right? So then they either both converge or they both diverge. Well, the original, the one I'm comparing it to, did converge. So by limit comparison test, the other one converges, right? So therefore, by limit comparison test, our original also converges. So on this next one, bulk comparison would be with the series n2 to the n over n cubed as our b to the n. Right. In other words, see how one of those n's cancels? 2 to the n over n squared, which by nth term test for divergence, don't forget about that one. If I run the limit on this, 2 to the n over n squared, see how we have infinity over infinity? So I could use L'Hopital's, which give me the natural log of 2 to the n over 2 times n. I'm still infinity over infinity, so I want to use L'Hopital's again. So I have ln of 2, and then I run the derivative of 2 to the n, which is another ln of 2 to the n. Take the derivative of the bottom, which is just 2. So now I'm left with infinity over 2, which is infinity. Well, the nth term test for divergence says when I run this limit as n goes to infinity, if I get something that's not 0, then it diverges. So we know this thing diverges by the nth term test. Okay, so the one we're comparing it to diverges. So now we're going to go ahead and apply our limit comparison test. So n 2 to the n over 4n cubed plus 1. This is all over. We're comparing it to 2 to the n over n squared. So we've got those will cancel there. So it looks like we've got n times n squared. I got n cubed over 4n cubed plus 1. Let's do this algebraically. Divide everybody by n cubed if we're doing this algebraic instead of L'Hopital's this time. Notice this will go to 0. And so we end up with, this ends up being a fourth, 1 over 4 plus 0, which is positive. So I say, oh, the original diverges, or I'm sorry, the one we compared it to diverges, therefore the original, by the limit comparison test, this n 2 to the n over 4n cubed plus 1 also diverges. This is a good you try problem, you guys, if you do want to pause the video. Well, for large values at n, we expect a and n to behave like 2n over n squared. In other words, 2 over n. But we'll take an even simpler one over n. And you can also use 2 over n. It really doesn't matter. But note that both of them are positive, right? I got positive terms on these. Again, with the comparison test, you got to have positive terms for all n greater than 1. So it does meet our criteria. So let's go ahead and we know diverges by the p series where p equals 1. Remember, if I'm less than or equal to 1 greater than 0, then it'll diverge by the p-series. And now we apply it, the test. We'll limit two n plus 1 over n squared plus 2n plus 1. This is all over 1 over n. So we got 2n squared plus n all over n squared plus 2n plus 1. I divide everybody by n squared, each term by n squared. I'll have 2 plus n over n squared, or 1 over n, over 1 plus 2 over n plus 1 over n squared. So that'll go to 0, 0, 0. So I'm just left with 2 over 1. Which again is positive. Therefore, the limit comparison test, the original also diverges as well, since that 1 over n diverged. All right, this is another good problem to pause the video and try, you guys. Let's go ahead and run through the solution here. For large values of n, we expect this to behave similar to 1 over 2 to the n. And so we're letting b of n be 1 over 2 to the n. That's the same thing as 1/2 to the n, right? And notice an, bn, these are all positive terms for all n greater than or equal to 1. And so it meets the criteria. So we're analyzing this 1 over 2 to the n. Does this thing converge or diverge? Well, by the geometric series test, right, we have r being 1/2. That's multiplying by 1/2 each time. So the absolute value of r is less than 1, greater than 0. It converges. This thing will converge by the geometric series test. And so now we can use the limit comparison test and what I'm going to do here is I'm going to solve this algebraically. That's because L'Hopital's is limited on this one. It's not going to help us out. I just keep getting the same derivative over the same derivative, which means I keep staying indeterminate in form. So instead, I'm going to divide everything by 2 to the n, do this algebraically. And I got 1 over 1 minus 1 over 2 to the n. Well, now that'll go to 0. And so this just ends up being 1 over 1 minus 0. So 1 over 1, which is positive. Therefore, it converges just like that 1 over 2 to the n converged by the geometric series test. All right, let's go ahead and check this one. Again, this is another good you try problem. If you do want to pause the video, try this thing first. And I do want you to know, even though you could actually use the direct comparison test on this. So just FYI, the direct comparison test would work here as well, but we're gonna continue practicing the limit comparison test. So we're gonna compare the series to, let's go with Bn being 2 over root n, which is 2 1 over root n by p series test with 1 over n to the p, so p here is a half, so p is less than or equal to 1 greater than 0. This will diverges. And so now we can applying the limit comparison test will yield and we got infinity over infinity here, so I'm going to go ahead and divide everybody by that square root of n. Do this thing algebraically. Notice this will go to 0, so I got 1 over 1, which is greater than 0. Therefore, by limit comparison test, also diverges as well. That's what we compared it to. Well, thanks so much for watching. Take a note. See you next time.